suppose we have three sets, A, B, C. And let us suppose that I have a function f that maps A to B. And let's suppose I have a function g that maps B to C. So why don't we draw a picture of this? Here's A. Here's B. Here's C. And why don't I suppose I have a couple of points in here. There's A1. There's A2. What we're going to talk about now is what's called the composition of functions. So first of all, let's complete this drawing here. So let's suppose this looks like this. And let's suppose that this looks like this. Okay, so this is the function f over here, and this is the function g over here. Now note, what we can do over here is we can talk about f of a1, and according to our picture over here, that sends us over to b1. But then what we can do is we can now apply the function g to this. So I can talk about g of f of a1. And that's going to be equal to g of b1. And that's equal to c1. So what we've done over here is we've actually composed two functions. There's another notation for this. Sometimes you'll see people write g and then they'll write a little circle of f of a1, and that's equal to c1. And note that what g composed with f does is that actually maps the set A over to the set C. So we can see in this example again, if I were to look at g of f of a2, well, a2 comes over to b1 as well, and that also takes us over to c1. And I could talk about g of f of a3, and a3 takes us over to b4. Okay, that's what f does. Then g takes it over to c2. Okay, composition of functions. So this naturally leads to two questions. If f maps A to B is 1 to 1, and G maps B to C is 1 to 1, is G composed with F, which maps A to C, is that also 1 to 1? Well, first of all, what we can do here is we can certainly consider a picture here. So let's send this over to here. And why don't we send that over to there? And why don't we send that over to there? So this could be F. And let's come over here and draw C. Let's give C some more points here. And suppose we had some relationship that looked like this. Okay, and this would be G. And we can see over here that this is clearly a one-to-one function. We can see over here this is clearly a one-to-one function. Okay, and I think that you will believe by looking at the picture, if I come over here, if I were to have that G of f of x is equal to G of f of y, does that imply that x is equal to y? Well, in this picture it certainly does. Okay, so at least the way that I have drawn this picture, it would appear that the answer to this is yes. Okay, but now, okay, so let's suppose if g of x equals g of y, then x is equal to y. And I'm going to say over here, this is by assuming g is 1-to-1. Incidentally, notice if this is true, if g of x is equal to g of y, well, remember g of x and g of y are in C, so this means x or y, okay, and I'll say in here, or y, this is actually contained in the set B. Okay? So if these are true, if g of x is equal to g of y, then x is equal to y. On the other hand, if f of, and I guess I need some other letters here, I'll say f of alpha is equal to f of beta, then alpha is equal to beta. And this is since S is 1-to-1. Okay. So we can clearly see then that if I were to have g of f of alpha is equal to g of f of beta, then alpha equals beta. And that pretty much proves it right there. It's just relying on the definitions. One more thing to consider. If f maps A to B is onto, and G maps B to C is also onto, is G composed with F mapping A to C onto? And the answer is yes. And again, we could come over here and imagine that we have something like this. So if it's onto, maybe we have a situation that looks like this. And now if this is onto here, maybe there are even less points. And of course, remember what the question is here. So if this is A, B, C, basically the question is, for any C that's contained in C, is there an A contained in A such that G of F of A is equal to C? And the picture really almost does it for us. If we pick any C in here, okay, because the mapping, and again, this is F, this is G, G is onto, so if I pick any C in here, we know that there is some B that maps to C. Likewise, because the mapping F is onto, we know that whatever B mapped to the C that we chose, there's got to be some A that maps onto it. The conclusion is that the composition of the functions is onto. Yes? Okay? Finally, and we'll leave this as an exercise, but consider the following. Suppose F maps A to B is one-to-one and onto, and G that maps B to C is one-to-one and onto. So the question is, questions, is G composed with F one-to-one and onto? And then question number 2, is the inverse of this a function? A little bit about notation. Remember what this is. If we remember the original composition of functions, recall that G composed with F maps A to C. So this thing over here, G composed with F inverse, that actually maps from C to A. And in fact, sometimes you'll find that the way that people write this over here is they'll say that G composed with F to the -1 is really the same thing as saying F to the -1 composed with G to the -1. And I ask you to think about that, and I'm going to leave it to you to prove this. It's not difficult. These are all kind of obvious. I think number one, we've really proven. Number one is really a result of the past two results. The answer to this is yes, of course. And as we've seen previously, if you have a one-to-one and onto function from one set to another, then clearly the inverse is a function. In fact, we don't even need to be onto for that.